We're going to continue with chapter 4, example 4-8. And right here they're asking us what is the voltage required to generate an I source of 1 milliamps. So if we go to Ohm's law, we know that I source is equivalent or is defined as voltage source over R total. So we have the I source and we can find the R total. So we have 1, 2, 3, 4 resistors. So we are going to add them to get 9.5 kilo ohms for our R total. So from here we can solve for B source. B source is just I source times R total. So we have 1 milliamp multiplied by 9.5 kilo ohms. So the milli and the kilo cancel and we get 9.5 volts. So the source, if we have a voltage source of 9.5 volts with these resistors, it will create a 1 milliamp current. In 4.9 it says calculate the voltage drop across each resistor. So the current across the series circuit, it is given. So it is, we can only use, the easiest way to do this is using Ohm's law to find the voltage across each individual resistor. Usually the way we label the voltage, if this is R1, then this will be called V1. This is R2, so it will be V2. This is R3, so it will be V3. So voltage is, using Ohm's law, is defined as current times the resistor that we are going to calculate the voltage drop at. So in this case it's 1 milli times 1 kilo ohm, so it's 1 volt. Then for the V2, the current stays the same because it's the same all across. The R2 changes to 3.3 kilo ohms, so we get 3.3 volts, and then R3 is 4.7, so it's 1 times 4.7. One thing to keep in mind here, and it's just important to remind you, we went over it when we're doing the lecture portion of this chapter 4, but the voltage drop across the resistor is directly proportional to the resistor value. What does this mean is that if the resistor is high, the voltage drop across this resistor is going to be high. As we see here, the largest resistor was 4.7, so the largest voltage drop was expected to be at 4.7 volts, and it was. Why? Because look at the definition. How do we calculate voltage? Voltage is the current versus the resistor. So the current, it is constant. The only thing that is changing is the resistor. So, and it's a linear relationship. So the higher the resistor, the higher the voltage drop across that resistor. Then we can calculate the voltage source. The way we calculate the voltage source is we calculate the voltage, the R total. We just add them up to be 9K. Then the voltage source is just the I times the R total, which is 9 volts. If we were to add this 1 plus 3.3 plus 4.7, we get 9 volts. So it checks. They are the same. So the voltage drop across this resistor plus the voltage drop across that resistor plus the voltage drop across this resistor, they better add up to 9 volts. Why? Because I start with 9 volts here, I drop 1 volt here, I drop 3.3 volts here, and I drop 4.7 volts here, to the point that when I'm here, I'm connected to ground. Ground means 0 volts. So after this resistor, my voltage left should be 0 volts. It's very important that we consider that. Another thing that I want to mention here is that when we are doing voltages, when we are calculating voltages, we want to give voltage a polarity, because voltage has a polarity. It has a direction in which the current flows. It usually flows, the conventional way is positive to negative. That is the way we are doing it. You see, this is a clockwise current direction for what we have. So I'm going to always assume that the resistor, the current enters this resistor through the positive side and leaves through the negative side. In here, it is easy to see where the current enters. and where it leaves it. There are going to be more complex examples where we are not so clear about it. So it doesn't matter, we are still going to give it a value, a polarity value, and if we keep it consistent, the math is going to take care of itself. For example, if I assume this and the current actually was going from here to here, the value that I would get, it would be a negative value. Then that indicates me that my polarity is wrong, that I have to flip it. Another way how to assign polarities is by the positive, the positive side of the resistor is going to be the one closest to the positive side of the voltage source. So since this is closer to here, it's positive. This terminal is closer to this terminal than this terminal, so that's why this becomes the positive. And it's important to remember that this positive goes with this negative. This positive belongs to that negative. You see here we have a negative and a positive at the same point, but they have nothing to do with each other. They are just saying that this to that, this to that. It's important to keep that in mind, okay? Now it says, what happens to the voltage source if the current is increased to 5 milliamps? So now we have the same resistor values, but now my I goes from 1 milliamp to 5 milliamp. So what do we expect? We expect that the voltage is going to be increased, assuming that the resistance is going to stay the same. Why? Because of the definition. Using Ohm's law, voltage source is equivalent to I times the R total. R total remains the same, but now I gets increased from 1 to 5. So it's just simple math to explain that if the voltage is going to be increased by a factor of 5 as well, and then we multiply it and we see that we get the 45 volts. Voltage source in series. So we have two different configurations for voltage source in series. We can have a configuration called series adding, where the voltage sources are connected in a way that they add up to a larger voltage source value. So that is the case we have for our TV controller, where we have two different batteries and they are aligned in a way that when you add 1.1 plus 1.1, you get a total of 3 volts rather than 0 volts, as we are going to see. So this is the example. We have 3 different batteries, and the first step is to identify which terminal is the positive and which terminal is the negative with respect to this battery. So we know that the longer section terminal of it is the positive, the shorter one is the negative, so we do that for easy. Then we choose a direction. I'm going to say I'm going to go from left to right. I'm going from left to right, yes, from left to right. So I'm going to go from here. So how do I do it? I'm going to write the value of the battery. In this case is 1.5 for all of them. And I'm going to write the sign in which I enter the battery. In this case, I'm coming from here. I put a positive because I'm entering through the positive. I go to the next one. I put a positive because I'm entering through the positive. And then here, a positive because I'm entering through the positive. So I get a total of 5.5 volts. So this configuration is considered a series adding configuration. It can be a different way. It can be a way that one of the resistors are connected in the opposite way, and those are called series opposing. The definition of series opposing is that resistors or batteries, not resistors, are connected in a way that its polarities are reversed. And if they are reversed, instead of adding, they are going to be subtracted, as the example right here. We have 3 batteries. They still be 1.5 volts. And now I'm going to assign the positive and the negative polarities. So this is positive, negative. This is negative, positive, positive, negative. So I chose my direction left to right. And now I'm going to say positive 1.5. Then I enter this battery through the negative. So I put a negative there. Then I enter this battery through the positive. So I put a positive there. So my voltage equivalent from these 3 batteries is just one battery, 1.5 volts, which means I have these 2 batteries that are doing nothing. So why to have it, right? So it's very important that you guys understand this when you are doing a design, how to connect batteries so that they can add up or subtract depending on what is the use for it. Okay, let's stop right here.